Hi folks, Chris McClure here. Now we're going to continue talking about characterizing distributions. Last time we talked about finding some measure of central tendency. For example, the mean, median, mode, mid-range. Today we're going to talk about characterizing the distribution by finding some measure of variation. In other words, some measure of spread. How spread out is the data? Okay, so let me pull up my pen. Okay. So our focus, though, is going to be on the standard deviation. That is the primary measure of variation that is used in statistics today. Okay. Now, before we get to the standard deviation, we will talk about one simple back of the envelope stubby pencil calculation that you could do as a means of determining variation. And that's just simply to take the maximum value of your data set minus your minimum value. So, if you had already sorted your data set when determining the median, and you're sort of going from smallest to largest, then you can simply identify that largest number and the smallest number and take the difference between those two. But just understand that it has certain limitations. In particular, it's very sensitive to extreme values, therefore it's not very useful compared to other measures of variation. Okay. Now, in the calculations to come, in particular for the standard deviation and variance, when we're looking to express our final answer, we'll observe the same rule as we did for the mean, and that's to carry one more digit of precision compared to the set of numbers. So if your set of numbers, for example, contain all integers, then you should express your standard deviation or variance out to one decimal place, for example. And when you are doing the few steps that go into calculating the variance or standard deviation, is to carry as much or as many decimal places as you can during the intermediate steps. And in particular, with today's calculators, you can actually probably put everything in there and have the calculator do all the steps. But if you have a more simple calculator and you have to do several steps, 2 or more steps, be careful that you don't round very much during the intermediate steps. Just carry as many decimal places as you can. Okay? And then only round your final answer. Now, here's the definition of standard deviation of a set of numbers. We use the letter S, and I write it like that because my S's look like 5s. Lowercase s, it's a measure of how much that the data values in your sample size or in your sample, that how much those data values deviate away from the mean. Here is the formula of how to calculate your standard deviation, the standard deviation of your set of numbers. Now let me try to explain this. What's going to happen is you're going to first compute the sample mean. That's what X bar is. And then you're going to go through and take each number in your data set, subtract the mean. And they call that difference a deviation. So when you take the mean and subtract it from the data value, you produce what's called a deviation. And then you square all the deviations, and then you add up those squares of deviations. and then you divide by the sample size minus 1. Now what we mean by the sample size is nothing more than the number of numbers, the number of values in your data set. You typically use letter n to represent your sample size, but you're dividing by n minus 1 instead of n, and I'll explain here in a few minutes why. Now, if that's all you do, you take the sum of the squares of the deviations, divide by n minus 1, then that would be called the variance. But then you you take the square root of the variance to get the standard deviation. Again, try to do as much of this in one single operation on your calculator as you possibly can. Now, here is kind of a shortcut formula here. If you're doing this by hand, this tells you that to calculate standard deviation, you can use this formula, which is equivalent to the previous one. What you do is you add up the squares of the data values, that's what sigma x squared is, multiplied by the sample size n, minus the square of the sum of the data values, and then divide by n times n minus 1, and then take the square root of that. This also will calculate your standard deviation. It's just a different formula which some people find handier. Hey, use whatever works for you, okay? So some important properties of the standard deviation. It's a measure of variation of all the values from the mean. So it's based on all the data values, and it's a single measure of variation for all the values relative to the mean. Now, you should never have zero or negative number for standard deviation. It's almost always going to be positive, never going to be negative, and only 0 if all of the numbers are exactly the same. If you have some outliers, the standard deviation suffers from the same sensitivity to extreme values as does the mean. So that's why a lot of times we take a look at our data set first, and we make a decision ahead of time as to whether to include any outliers. Now, there are some different philosophies when it comes to outliers, and we'll talk more about that later, but I'm not going to tell you whether you should keep your outliers or not, but understand if there are outliers that, meaning some extreme values relative to the rest of the numbers, then those outliers could affect the mean and standard deviation. One of the advantages of the standard deviation is that it carries the same units of measure as for the original data set and for the mean. So if all your numbers are miles per gallon for different vehicles that you had measured, well, your mean, meaning your average miles per gallon, will also be, well, miles per gallon for units. And same thing with standard deviation. It will also carry the same units of standard deviation or of miles per gallon. So a real quick example of how to calculate standard deviation by hand. Suppose that we've got these four numbers, 22, 22, 26, 24. A real simple example. I'll show you here in a minute how to use your calculator as well, but to do this by hand, first you need to calculate the mean. Well, to calculate the mean is just going to be equal to the sum of those of those four numbers divided by the four numbers there. Now 22 plus 22 is 44, plus 50 is 94. So you get 94 divided by 4. Now 4 goes into 9 2 times with the 1 left over. 4 goes into 14 3 times with 2 left over. 2 fourths is 0.5. So 23.5 is your sample mean, x bar. So now what we'll do is take each number and minus x bar to give you these deviations. 22 minus 23.5, which will be negative 1.5, and square that. So you have negative 1.5 squared. And then do that again for this next one. 26 minus 23.5 squared, so that's 2.5 squared. And here we've got 0.5 squared. Add up those squares of deviations, and in the denominator, the sample size was 4, minus 1 is 3. So we'll divide by 3, and then take the square root of that. Now, in the numerator, if you added up the squares of these deviations, that worked out to be 11. So you have 11 divided by 3, take the square root of that, and you get approximately 1.9149, which should be expressed to 1.9. One decimal place beyond the level of precision expressed in the numbers themselves. Okay? Now, I'm going to jump over to my calculator here. I brought my graphing calculator. Now, some different ways that you could do this. Well, I'll show you one main way and some different ways in future lectures. Now, what you do here in your, I got a TI-84. Let me just kind of show you. This is the home screen here with the blinking cursor. Now, what I want you to do is to go into your stat menu. Stat as in statistics. Click on stat, and then within the edit submenu, you'll choose the first option, which is edit. As in, edit your lists. Now we're going to go into this first column, which has the label of L1. Now to clear out that list, we can up arrow to that column header and hit clear. And then down arrow, and you'll see it's cleared out. So let's just input some numbers, like 22, 23, 36, 21, 28, 17, and so forth. So each time you input your number, hit enter. And when you're done inputting your numbers, and then you can go ahead and quit out of there. And then if you wanted to calculate the standard deviation of that list of numbers, then you can go into the list menu. You have to hit the second button and that stat button, which will give you actually the list menu. And then right arrow over to the math menu. And then go down to option 7. Standard deviation. Go back into your list menu and select that first list, or whatever list that you use to input your number. Close parenthesis, hit enter, and there is the standard deviation of that list of numbers. Okay? Something else that you could do is you go into the stat menu itself, right arrow over to the calculate menu, and then select number 1, one variable statistics, and hit enter. And you see that S sub x, that means sample standard deviation. And notice it's the same number. Okay? That we could come up with. So 2 different ways of having your calculator do standard deviation for you. So now you know how to calculate standard deviation by hand and using your calculator. Now, there's going to be an important relationship between range and standard deviation. And it's based on the idea that for any set of numbers, and the larger the more applicable this is that about 95% of the numbers in a data set will lie within about 2 standard deviations of the mean. Meaning, if you were to calculate the sample mean and the sample standard deviation for a list of numbers, all right, and suppose, and I'll just illustrate this on a real number line, suppose that this is your sample mean, and then you were to add 2 standard deviations, and let this one be x bar plus 1 standard deviation, and let this one be 2 standard deviations. And then if you were to go out to the left 2 standard deviations, so x bar minus 1 standard deviation, x bar minus 2 standard deviations. So for example, suppose that we've got a sample a sample with a mean of, say, 10 and a standard deviation of 2, just to make it simple. So that means that we have 10 here, we've got 12 here, we've got 14 here. Because here we've added 1 standard deviation to the mean, here we added 2 standard deviations. Going to the left, we'll subtract 1 standard deviation, subtract another standard deviation. Now what we're going to say here is the data set that produced this mean and that standard deviation, about 95% of the numbers in that data set we would expect to fall between 6 and 14. Okay? So here's the range rule for the thumb, or it's a rule of thumb for interpreting a known value of the standard deviation. Basically what we're going to say here is that when you have an observation that is beyond 2 standard deviations of the mean, we would call that an extreme or unusual value. Okay? So anything that's below the mean minus 2 standard deviations, or anything above the mean plus 2 standard deviations, would be considered unusual. Again, we expect about 95% of the data values to be within 2 standard deviations of the mean. So we're talking about, if we go back, let me show you this picture here. This one right here. We've got the mean minus 1, minus 2, and plus 1 and plus 2. There's actually 4 here. So you would expect almost the entire set of numbers to cover these 4 standard deviations. So it'll be roughly true that if you were to take the minimum value of your data set and your maximum value of your data set and take the difference, maximum minus minimum, that will give you the range, and divide by 4, that'll actually give you approximately 1 standard deviation. And that is this rule right here that says that 4 times the standard deviation is approximately the range, or you can estimate the standard deviation by taking that max minus the min, dividing by 4, and that'll be a very rough estimate of the standard deviation of that data set. Okay? So that's one way of checking your work when you do your computation. Let's take an example here. Suppose that we take a sample of 40 chocolate chip for cookies. Chocolate chip cookies. Chips Ahoy chocolate chip cookies. We're going to count the number of chocolate chips in each cookie. So each chocolate chip count represents one observation. And we're going to do that for 40 cookies. So we have 40 numbers. Each number is the number of chocolate chips in each cookie. And each of the numbers in your data set will be an integer. So it doesn't really make sense to have a 0.0. It's just going to be some integer. And then you can calculate the mean. And it turns out for this example that 24.0 is the mean. It is appropriate to have one decimal place in the expression of the mean when you have integers for your data values. And your standard deviation in this example turns out to be 2.6. So let's go ahead and write that down. X bar sample mean is 24.0 and standard deviation is 2.6. So if you were to take X bar, we'll do it over here, X bar minus 2 times the standard deviation, that would be 24 minus, now 2 times 2.6 is 5.2. And what is that? That's going to be, what, 18.8 if we did that, right? If you were to take the sample mean plus 2 standard deviations, that would be 24 plus 5.2. That would be equal to 29.2. So we would expect almost all of the cookies to have between 18.8 and 29.2 chocolate chips. Okay? So if we were to have a cookie that have less than 18.8 chocolate chips or greater than 29.2 chocolate chips, meaning because there's an integer value for a number of chocolate chips. If we had a chocolate chip with either 18 or below or 29 and above chocolate chips, or actually over 29, so 30 and above chocolate chips, we would consider that an unusual observation. So if we have a cookie with 30 chocolate chips that's greater than this upper bound, we would consider that an unusual observation. So that's what they're talking about right here. So whenever you have a problem and what you're being asked, hey, whether this observation is unusual, then all you need to do is take the sample mean plus or minus 2 standard deviations, and so you add 2 standard deviations, subtract 2 standard deviations, and if your observation is below or above that range, then you do have an unusual observation. Now, we know how to calculate standard deviation now. It might be tempting to compare standard deviations between two data sets, but be careful. It might be appropriate if you have two data sets with the same mean and the same sample size. But if you don't have the same mean or the same sample size, then you have to be super careful. And we'll take a look at the coefficient of variation. It's a better way of comparing the amount of variation relative to the mean, instead of simply comparing standard deviations. Okay. So the very last slide of this presentation, I'll show you briefly how to compute the coefficient variation for your data set. Now, we had seen how to calculate your sample standard deviation, S. And it looks similar to this, but what we've got going on here is the population standard deviation, given by the Greek letter sigma. Now remember that mu was the population mean. Greek letter, right? And we're using a Greek letter sigma to stand for the population standard deviation. We typically, in statistics, use Greek letters to represent the population parameter. And we use typically lowercase English letters to represent sample statistics, which are used to estimate the population parameters. Now, if you happen to know the measurement for every individual in the population, then you could calculate the population mean and then take each individual's measurement minus the population mean, add up those deviations, squares, I should say, square those deviations, then add them all up, divide by the total population size, which, by the way, is capital N. Capital N is the population size. And then take the square root of that. And that'll give you the population standard deviation, sigma. But I'm here to tell you now that this is almost never known in reality. So we use we use S, our sample standard deviation, to approximate sigma, to estimate, I should say. We use it as to estimate the parameter, just like we use X bar to estimate mu. Okay? And that leads us into a discussion of inferential statistics, which will be in Chapter 4. Okay. Now, from time to time, we'll talk about variance, and variance is nothing more than the square of the standard deviation. So if you see S squared, that means that you have the sample variance right here. If you see sigma squared, that means population variance. And of course, S squared, sample variance, is used to estimate sigma squared, population variance. So just to recap our various pieces of notation for variance, S is sample standard deviation, S squared is sample variance, sigma is population standard deviation, and sigma squared is population variance. Now, the reason that when we calculate the sample standard deviation, that we divide by n minus 1 instead of n, is that this gives us what is called an unbiased estimator. And without getting into the mathematical details, that means that this is going to be a better estimator of the true population standard deviation compared to if we were to just divide by n. Okay? We'll leave it at that. So now that you know the basics of standard deviation and variance, again, if you are interested in knowing about why we divide by n minus 1, it has to do with the fact that there are only n minus 1 independent values. Remember that we had used n or all of the data values to determine X bar. All right, and then we're going to take each X value divided by, or excuse me, a minus X bar. But the thing is that when you know X bar and you know all but one of the data values, then I could tell you what that other data value is because I know X bar. So that's why we say that only n-1 values can be freely assigned any number before the last value is determined, because of the fact that we have x bar, the sample mean, as part of the calculation for sample standard deviation. And that's the reason that dividing by n-1 makes S bar, or makes S an unbiased estimator of the sample standard deviation. Well, S is the sample standard deviation. We're using S to estimate sigma, the population standard deviation. So divided by n-1 is what makes S an unbiased estimator of sigma. Okay. Anyway, I'll leave it at that. If you are still curious, then we could have a separate discussion on that, and I'll point you in the direction to do some reading. Now, we're going to be talking about certain distributions that are bell-shaped, in particular the normal distribution, but this applies also to the t-distribution and other sort of distributions that are approximately bell-shaped. And this rule that we're going to talk about is the 68, 95, 99.7% rule. That says that, if you know the mean and standard deviation for that distribution, that about 68% of the values in that distribution, whether we're talking about a sample, large sample size, by the way, or a population, that about 68% of the values of that distribution will fall within one standard deviation of the mean. So if I measure the height of a bunch of young men, and it turned out the average height was 68.2 inches, and the standard deviation, let's suppose it's, 2.1 inches. Well, I could tell you that about 68% of the guys in my sample will have a will have a height between, take 68.2 minus 2.1, you get 66.1 inches. On the low end, 68.2 plus 2.1 is 70.3 inches. So about 68% of the guys in my sample will have a height between 66.1 and 70.3 inches. About 95% of the data values will fall within two standard deviations. So in this little example here, 68.2 plus 4.2 is, actually let's subtract. 68.2 minus 4.2 will be 64.0. So there it is on the low end. If you were to take 68.2 plus 4.2, you would have, 72.4. So there we've got the mean plus or minus 2 standard deviations. So we would expect about 95% of the guys in my sample, or in the distribution as a whole, will fall, or will have heights that fall between these two numbers, between 64 and 72.4 inches. And we would expect that about 99.7%, so nearly all of the data values, will fall within 3 standard deviations. Take 64 minus 2.1, you get 61.9 inches. 72.4 plus 2.1 is 74.5, so 74.5. So there we've got the mean plus or minus 3 standard deviations. So we would expect 99.7% of all the guys in our sample to have heights between 61.9 and 74.5 inches. Okay, so that's an application of the 68, 95, 99.7% rule. Here's a picture of it with more precise numbers. Now here's the mean right here. Now if you were to go out one standard deviation below and above, you're going out 34.13% of the distribution below and 34.13% above. So together you have 68.26% of the population within one standard deviation, or 34.13% of the observations between the average and one standard deviation above. Now, if you were to take a little bit of arithmetic, you see that 50% of the population is above the mean, is above average, and 50% is below. Okay. Now, if you were to take 50% minus 34.13%, little bit of rough math here, 34.13%, then you would have what? 15.87. As in 15.87% of the distribution above one standard deviation of the mean. And 15.87% of the distribution below one standard deviation below the mean. For example. Now, if you were to add up these percentages here, so 34.13% plus 34.13%, 68.26%. And then add up the 13.59% plus 13.59%, you'd have what, 27.18%. And they'll do a little bit of arithmetic here. So you'd have 95.44% of the population between -2 and +2 standard deviations relative to the mean. So that means that about a little over 2% of the population is below 2 standard deviations below the mean, and a little over 2% of the population / distribution is above 2 standard deviations above the mean. Alright, moving along here. Now, here's an interesting theorem postulated originally by this guy and then proven later not only by himself but by several other people, but it's attributed to Chebyshev, famous Russian theoretical statistician or applied mathematician. But here's what his theorem says, is that the proportion / fraction of any set of data, any set, so this applies to any distribution, lined with so many, call it K, standard deviation, so K could be 1, 2, 3.5, whatever. So lying within K standard deviations, the mean is always at least whatever 1 minus 1 over K squared is. And you could express this as a decimal or as a percent, where K is any positive number greater than 1. So K is greater than 1. So, for example, suppose, though, I want to know that, okay, what fraction of my data / distribution / population will fall within, say, 1.5 standard deviations. So let K be equal to 1.5, which, by the way, is 3 halves. Now take 1 minus 1 over 3 halves squared. That's equal to 1 minus 1 over 9 fourths. And that would be equal to 1 minus 4 ninths. And that would be 5 ninths. Let me pull out my calculator here. There's my calculator. Let's do, I'm going to clear the screen here. 5 divided by 9. Okay, approximately 55.6%. Oh, okay. So approximately 55.6% of my distribution, of my population, set of data, whatever you want to call it, will be within 1.5 standard deviations of the mean. Okay? That's what that says. If you want to know how much of your data will be within 2 standard deviations of the mean, well, 1 minus 1/4 is 3/4, so at least 3/4 of your data will be within 1 standard deviation. And it's not just 3/4, it's at least 3/4. Just like at least 55.6% of your data will fall within 1.5 standard deviations. If it's 3 standard deviations, then 1 minus 1 over 3 squared is 1 ninth, or 1 minus 1 ninth, which is 8 ninths, which is approximately 89%. So at least 89% of your data will be within 3 standard deviations of the mean. And this is not just for those nice bell-shaped distributions, but this is for any set of data. It's for any distribution. So it could be a really screwed up multimodal, heavily skewed distribution. Doesn't matter. This is a nice general result, and one of the reasons why it's so important. Here's another example. Suppose that we have a set of IQ scores for people, and typically the IQ is adjusted so that the mean is 100 and standard deviation is 15. Well, we know that at least 75% of the IQ scores will be within 2 standard deviations of the mean. Now, 1 standard deviation is 15, 2 standard deviations is 30. 100 minus 30 is 70, 100 plus 30 is 130. So, at least 75% of the people will have IQ between 70 and 130. And likewise, we see that about 89%, in particular 88.9%, that's 1 minus 1 over 3 squared, which is 8 ninths. If you were to do 8 divided by 9, you'd get approximately 88.9%. So about 88.9% of human population, randomly selected, will have IQ scores within 3 standard deviations of the mean of 100. Now, 1 standard deviation is 15. 3 times 15 is 45. So if you were to take 100 minus 45 and a plus 45, you get 55 and 145. So 88.9% of the population will have IQs between 55 and 145. At least 88.9%. Now, here's the last slide, and I'm just going to tell you this in passing, that if for some reason you are comparing standard deviations or variances between 2 data sets, and those 2 data sets don't have the same average value, then you should not be comparing those measures of variation against each other. But what you could measure or compare against each other is the coefficient of variation. What you could do is take, for each data set, the sample standard deviation divided by the sample mean. And if you want to express it as a percent, then go ahead and multiply by 100%. And do this for each data set. Then you could talk about, which data set has more variation and which has less variation. Okay? And with that, that is it for today. And we'll see you next time. I've got homework posted. If you are having any issues, by the way, with using StatCrunch for anything, please let me know, and I'll be happy to either respond in email or record a short video on how to do something, okay? So we'll see you next time. Take care.